Next, we want to look at how the position, the velocity, and the acceleration of an object undergoing simple harmonic motion changes. For this problem, we will consider a mass on a spring. So the spring here is oscillating back and forth, and when the spring is stretched, a force pulls the mass back towards the spring, and then when the spring is compressed, then the spring pushes the mass away from the spring. For this reason, there's always a restoring force that points towards the center point for the mass. So now let's think about what this means for the position, the velocity, and the acceleration of the mass on a spring. We start with our spring fully stretched. The black line here is the position as a function of time, so the spring is pulled all the way down. The moment we release it, the velocity of the spring is zero. It is stationary at that very moment of release, and then it starts to move up with a positive velocity. If we were watching the spring for a long time, we would notice that at the end of its run, there is a split second where the mass stops moving and the velocity is zero. Okay, so the position here is negative and the velocity is zero, so what is the acceleration? Well, as the spring is fully stretched, the force is at a maximum. So if the force is at a maximum, then the acceleration will also be at a maximum. Lastly, if we want to think about the energy, then the potential energy will be at a maximum because the spring is fully stretched, and the kinetic energy is zero because the velocity is zero. All right, so let's follow the mass as it travels to the center point. So we go to this second line here. So when at this point the mass is moving quickly and our position is at the center point. So our position here is zero. The velocity is going to be at a maximum, so it's moving up, and the spring has done work to the mass from the stretched point to the center here, so the velocity is at a maximum. And so also if the velocity is at a maximum, then the kinetic energy is at a maximum. Notice the velocity here is positive, so our blue line here is positive because the mass is moving up. So the acceleration, though, now that's going to be zero because the displacement is zero, so the spring is not providing any force. So that means that the potential energy also is going to be zero because, well, there's no force here. Okay, so as we continue through, now our mass is at the top of its oscillation, so it's up at the top of its run. So that means that the displacement is positive now, and so that means the velocity is zero because it has come to a stop for a brief moment, and the acceleration is now pointing down, and so that means that the acceleration is negative and it's at a maximum. So the potential energy is again at a maximum, while the kinetic energy is zero. We continue back to the center point, and now our position is zero. The velocity is negative and at a maximum, right? It's moving down now, so the velocity is negative, and the acceleration is zero again because there's no displacement and hence no force from the spring. So now we return to back where we started, so where the spring is fully stretched, and we have a negative displacement, a zero velocity, and a maximum positive acceleration, and a maximum in potential energy. And notice that this sequence will continue on and on as long as we're undergoing a simple harmonic motion. Okay, so we've gone through the oscillation qualitatively, but we want to analyze the position, the velocity, and the acceleration quantitatively. So we need to look at this a bit more carefully. So here our mass has a position that is a times the cosine of omega t. This is the description that we used in the last video, and a is the amplitude and omega is the angular frequency. So what's the velocity? Well, we know the displacement is at a maximum, then that means that the velocity is at a minimum, so the velocity should be phase shifted. So our velocity turns out to be minus a times omega times the sine of omega t. It is negative because our mass starts moving down, so it needs to be negative, times sine, and the amplitude is the original amplitude times omega. This should make sense because the larger the amplitude, the faster it goes, but also the larger the angular frequency, omega here, also the faster it goes, right? So if your omega gets very large, then it's going to oscillate back and forth very quickly, so the velocity is going to increase. So notice, yeah, this omega matters, how fast the oscillator goes. I know this isn't a calculus-based course, but the velocity is the derivative of the position, so you may be able to see that if we take the derivative of a cosine omega t, we get the negative omega a times sine omega t. For acceleration, it's the negative of the amplitude times omega squared times the cosine of omega t. It is cosine because the acceleration is a maximum when the displacement is a maximum, so both will be cosine. However, when the displacement is up, the acceleration will be down, so that's why we need a negative sign. Now we know the acceleration, so for a mass on a spring, the force will be the k, the spring constant, times the displacement. The position x is a cosine omega t, so we can rewrite the force for our acceleration equation as the mass times negative omega t squared times a cosine omega t, and a cosine omega t is the position x. So that means that negative m omega squared is equal to kx. So the x cancels out, and we can then solve for omega as a function of k and m. And we get that omega is equal to the square root of k, our spring constant, divided by the mass. That means that the angular frequency is the square root of k over m. So if we know omega, then we know the period is 2 pi over omega, and we can then find the frequency. So notice the frequency is proportional to the square root of the force constant. So the higher the force constant, or the stronger the spring, the faster it oscillates, while the larger the mass, the slower that it oscillates. Also notice that the position here, so the amplitude, that has completely been canceled in our formula here. So this is another reminder that for simple harmonic motion, it's independent of the amplitude. So the frequency is independent of the amplitude. All right, so you have some questions to do, and next we're going to work through some examples. Good luck.